Okay, welcome back to lectures on engineering mathematics 2. So, this is lecture number 8 on surface integrals, and we will continue because we have already covered the surface integral for scalar functions, and today we will introduce the idea of vector functions for surface integrals. So, we will cover this orientable surfaces first, and then we will come to this flux integrals, which is the surface integral of vector field. So, just to recall what we have covered in the last lecture, that was the surface integral of g on over this S over the surface S, and the idea was that this function g is being integrated over the surface S, and this surface integral will be converted to the simple area integral or the double integral, where this r is the projection of this surface. So, for instance, this is the surface here, and this will be projected on one of the coordinate axes. So, suppose here on this x y plane. So, not the coordinate axis, it will be projected on the coordinate planes. So, suppose this surface is being projected on this x y plane, then we have this r here on the x y plane. So, this double integral will be evaluated on this region r in x y plane, and there is an additional factor here because of the difference between this curvature of the surface and this plane area on this x y plane. So, that factor will be coming, and then we have a simple double integral, that is d a. So, as written here, r is the projection of S on the x y, y z or z x plane as per the convenience, because we have to also look that this del f, which is the perpendicular to the surface, should not be perpendicular to this p, which is the unit normal vector on the plane where we have projected the surface. So, with this idea we can now go for more general integral, more general surface integral. So, before that we have to introduce here this orientable surface. So, it is a smooth surface which we have already discussed. The only difference is that we will add here. So, if the two sides may be painted in two different colors of a given surface, then we will call this as a orientable surface. So, with the help of examples we will explore more. So, for instance, here we have these two orientable surfaces. So, this is the cylinder, we can paint with two different colors, the inside and the outside. The more formally, mathematically, the idea is that we can have a normal at any point, and that will be in the two directions. So, one will be in the inner direction and then will be the outer normal. So, similarly, here for the sphere as well, we have the two normals at any point. One is the outward normal and the another one will be the inward normal. So, at any point of these surfaces we have a unique normal at any point, and they will have two directions. One will be just the other of the direction of the previous one. But if you consider this Mobius stripe, then the situation is not so what we have here for such surfaces. So, for instance, here if I pick this point and then this will be kind of normal at this point, but if I go along with this and then come back, then I will be on the other side of this stripe. So, basically the idea is that this geometry here you cannot paint with two different colors, or meaning that we do not have two distinguishable surfaces for such a geometry. So, we will not consider this for such surface integrals which we are going to cover today. So, always we will have two different two distinguishable faces of or surfaces of a given surface. Okay. So, having that, we have the flux of a vector field f through a surface S, which we will discuss here in this lecture. So, the flux of a vector field f across the orientable surface S. So, orientation is important because we will be considering the normal in two directions. So, in the direction of this n, unit normal to S, and this is given by this integral here. So, we have this flux integral, the f dot n, the component of this f in the direction of the normal is being integrated over the surface S. So, this is what we call the flux integral or the flux of a vector field f through a surface S. Geometrically, a flux integral is the surface integral over S of the normal component of f of the vector field f. So, if this f is continuous velocity field, for example, of a fluid, and the rho is the density of the fluid at a point x, y, z, then such a flux integral, for instance here rho times this f dot n, because this is exactly the component of this velocity field across this along this normal to the surface. So, this will tell us that the mass of the fluid flowing across S per unit of volume. So, it has several other applications, this integral, the flux integral. So, we will evaluate this for some simple examples, but now the idea is that how to evaluate, and this is exactly being translated from the previous lecture, where we have discussed already that how to evaluate surface area, how to evaluate a scalar function over the surface, and here we will continue this again for such a more general integral. So, the evaluation, we assume that the S, the surface S, is a part of this level surface f x y z equal to c. So, whatever, if our surface is given z is equal to f x y, we can write, or let us take g x y, then we can define z minus g x y as the new function, this f x y z, and for this f x y z function we will consider equal to 0 as a special case of this level surface. So, that will exactly represent the given surface, the equation of the given surface. Because here once we have taken this equation of the surface f x y z equal to constant, then this n, the unit or the normal may be taken either of the two unit vectors, as I discussed before that there will be two directions for the unit vectors. So, this we can compute, because we know that with the help of the gradient. So, gradient of f will pointing out in the normal direction of the given surface, and then we can normalize to have the unit vector. So, this n is nothing but the plus minus the gradient f and its magnitude. If we divide by the magnitude, this is the unit vector. And the flux now, so f dot n, so this is the n for the given surface f, gradient f and its value there to have this unit vector, and this is the factor which we have already discussed, because now we are integrating over the projected area which is being projected on one of the coordinate planes. So, this factor will be the additional factor to compensate that curvature of the surface, and then this is being integrated over this projected R. So, this integral we can evaluate, we can simplify it more, because we have this the magnitude grade f and the magnitude grade f. So, this can be further simplified. So, the flux integral which was written there, that f dot this n d sigma can be evaluated with the help of this f dot grade f over grade f dot p and integrated over this projected region R. Okay, well, so we can now go through the problems. So, the first problem, we want to find the flux. So, the f is given as y z plus z square and outward through the surface S. So, there will be inward and the outward directions. So, here we are going to cover the outward in the outward direction. So, we have the f, the vector field is given, and the surface S is cut from the cylinder. So, we have I square plus z square as cylinder, that means it is parallel to the x axis. The axis of the cylinder is the x axis, and only in the positive for positive values of z. So, we are not going the negative values of z. So, it is like a half cut of the cylinder, and then to get the solution. So, this is the situation here, we have the x axis. So, this is the cylinder which is cut from this x is equal to 0 to x is equal to 1. So, here we have this x is equal to 1, and this is of course, the x is equal to 0 line. So, then this is the surface S, and as discussed before, to get this surface area to get the surface integral, we have to project it on the one of the coordinate planes. So, here naturally we will project here on the x y plane, because if we project on the other planes, that condition which we have in the denominator, the dot product, that may become 0. So, we will or will become 0 actually. So, here in this case we will project on the x y plane, and so we have the surface f x y z equal to c. So, f x y is basically this x is y square plus z square minus 1, or f we can take here x y z is equal to y square plus z square, that surface equation. So, having this, we can compute the outward normal. So, with the plus sign it will be the outward normal, and we take the minus sign, that it will be the inward normal, that we can realize from this expression. So, the grad f will be the partial derivative of this with respect to x, which is 0. So, we have the 0 ith component, then we have the partial derivative with respect to y, that means 2 y j, and then we have 2 z and k. So, this is the grad f, and then we can divide by its magnitude. So, we have 2 y j and 2 z k. So, the magnitude is 4 y square plus z square, and this y square plus z square on the surface on the cylinder, that is given 1. So, we have here just 2, and then that means the 2 will also get cancelled. So, we have this outward normal, this y j and plus z k. So, the p concerning that vector p, which is the normal to the projected plane. So, here we are talking about that this surface is being projected on the x y plane. So, that means this p is going to be k. So, this is in the direction of the z axis. So, p is simply k, and then we can compute this d sigma, that is the differential element on the surface, with the help of this expression. So, we have grad f and the again magnitude of grad f dot p. So, the grad f magnitude and this grad f, the dot product with the k in this case. So, the grad f is already given y j plus z k. So, here in the denominator we are going to have 2 z. So, grad f is 2 y j plus 2 z k, and then when we do this multiplication with k. So, this second component will survive, that means the component with the k, that is 2 z. So, gradient 2 z, and then this is already we have seen that the magnitude of this grad f is 2. So, we have 2 over 2 z, and z we are talking about the positive, we are going for the negative direction there. So, it is just positive. So, we have 2 over 1 over z, 2 will also get cancelled, 1 over z, and this dA is the differential element on the x y plane. Well, so we need to get also the f dot n. So, the f is given y z plus z square. So, we have f as y z j plus z square k, and its dot product with this n, the unit normal, that is given here y j plus this z k. So, if we put the dot product, we have this y a square z, and then here we have z cube. So, that means here if we take the common z, then we have y square and plus z square, and on the surface this is y square plus z square is 1. So, we have simply z there. So, having this f dot n z and d sigma is also given. Now, we can compute the surface integral. So, the flux through this S, that is f dot n and d sigma. So, d sigma element is 1 over z and this f dot n is z. So, if we multiply the two z and then 1 over z, we have just 1. So, this will be integrated over the projected plane. So, what is the projected plane? Projected plane is in the xy plane, and this is just the square with 1 and the 1 here. So, we have this is from here to here 1. It is actually rectangular, because here you have the minus 1 as the y component, here 1. So, this is 2. So, this is 2 in 1 in the direction of x, and then with in the direction of y, this is 2. So, this is 1 here and this is 2 there. So, this projected area will be simply the area of the projection. So, that is the area of this rectangle. So, without a further calculation, we can get this area of the rectangular, which is 2 here. So, it is clear we need to compute this f dot n. For that we need n, and can be computed from the given equation of the surface. We need this differential element, which is standard, we have done in the last lecture as well. So, this again with the help of this f and this p, which depends on which coordinate plane we have considered for the projection, and then this is 1 over z dA. So, the value is 2 of this flux. Okay, so, the next problem, if we want to evaluate this integral here. So, if we want to evaluate this integral f dot n d sigma over this S, where this S is the portion of this plane which is in the first octant. So, we have this plane and we are considering only the first octant of that plane for this surface. So, again the same process, the f is also given, we need to compute f dot n, we need to compute this differential element, etc. So, the solution, we take f, the surface here 2x plus 3y plus 4z, and the given surface is just the level surface of this function. So, the grad f we can compute now, the partial derivative of this with respect to x, that is 2 here, that partial derivative 3, then partial derivative with respect to z is 4. So, 2i, 3j and 4k is the gradient of f, and the unit normal vector. So, gradient of f, and we have to divide by its magnitude, that is square root 29, and we have this vector 2i 3j plus zk. Then we also need this f dot n. So, f is given there and n here and n is here. So, we can compute this f dot n now. So, 1 over square root 29 will be coming, and then here 2, there we have 6. So, 12 z, we have 3 here and then 6 there. So, we will have 18 there, and we have 4 and we have 3. So, we have 12, we have 12 and this y from there. So, this is f dot n, and the next we have this element here d sigma, which is gradient f divided by this product. So, we need to compute this as well. So, the gradient f is computed here, we have already computed its magnitude, that is square root 29, and then the gradient f with this dot product with the k, because here we are projecting on this xy plane again. So, that is the normal to the xy plane, we have here the k. Here we have the possibility to project this plane on either yz plane or zx plane or xy plane. So, we have taken this xy plane. In that case, we have taken this k here. If we take the other coordinate plane, accordingly this vector p, which is taken here k, will change. Okay, so, this is usually we denote the unit by this hat. So, this p is taken this k hat in this case, and we got this element square root 29 by 4 and dA. Now, moving further. So, we are projecting on the xy plane as discussed. So, what is the projection on the xy plane? So, this was the situation. This is the plane here 2x plus 3y plus 4z equal to 12, and then we can project this either on this xz plane, or we can project on the yz plane, and now in this present situation we are projecting on the xy plane. So, as you can see, this projection is going to be a triangular shape. That means, the projection R will be bounded by this x axis, will be bounded by the y axis, and of course, from here, because we have projected already. So, z will become 0 there, and we have 2x plus 3y equal to 12. That will be the line here connecting the two axes. So, we have the this situation now for the projection. This is the x axis, and then we have y axis there, and this is the line 2x plus 3y equal to 12. So, we will be doing the integral over this triangular shape of for this surface. So, we have f dot n is given by this. We have evaluated already 1 over square root 29 and 12 z plus 18 plus 12 y. We have also this surface, that is the given surface. This element also we have evaluated, d sigma is equal to square root 29 by 4. So, these evaluation we have done. So, we are ready now to compute this flux integral, and the domain also we have discussed that this is the projected domain where we will be integrating now a double integral. So, this surface integral over this R is this region given here, the projected one. So, we have 1 over 29, that is f dot dn, f dot n here, and 1 over 29. So, this 12 z, because we are projecting in x y plane, the z has to be replaced from the given surface. So, we have there this 4 z as 12 minus 2 x minus 3y, 12 minus 2 x minus 3y. So, this 12 x z was written as 3 into 4 z, and this 4 z from this equation of the surface is replaced by this 12 minus 2 x minus 3y, and then we have 18 and we have this 12 y. Then this differential element is replaced by this square root 29 by 4 dA. So, we have the simple the double integral which has to be evaluated over this given region R. So, concerning the limit, we have to propose the limit. First, this simplification will lead to this expression 54 minus 6 x plus 3 y, and then the limit. So, first let us talk about the limit of the y. So, y is moving from the 0. So, y from 0 to, from here we can get, that means 12 minus 2 x and divided by 3. So, 12 minus 2 x divided by 3, and for x we have from 0 to, this is what we will get from here. So, when we put this y 0, we have 2 x equal to 12, that means here x is equal to 6. So, this is 6 0 point. So, the x is moving from 0 to 6, x is from 0 to 6, and y is from 0 to this line where y we have computed as 12 minus 2 x divided by 3. So, this double integral one can evaluate, and the value is coming as 138. So, this is the simple double integral which we have evaluated already in integral calculus. Okay, so, another example where we will evaluate this surface integral over this S. S is a portion of the surface of the cylinder. So, we have again a cylinder, x square plus y square is equal to 36, and the z direction, the axis is parallel to the z axis. So, we have this 0 to 4, the z is varying from 0 to 4 and it is included in the first octant. So, here we want to evaluate the surface f dot n, surface integral d sigma, where f is given by this expression. So, again we will consider, we will take this f, the given surface x square plus y square, that is also fine if we take x square plus y square. 36 is not playing any role for the evaluation of the gradient, for instance. So, here we have the situation, we have x axis, we have y axis, we have z axis, and this is the cylinder which is along this z axis, and it is varying from the z equal to 0 to z equal to 4. Well, so then we have grad f is 2x the ith component, 2y the jth component, and the absolute value of this grad f we can evaluate. So, 4x square plus 4y square, and x square y square is 36. So, 4 into 36, which is coming 12. So, the grad f is 12, the magnitude of grad f is 12. Then the unit normal vector, again the grad f and divided by this magnitude 12. So, grad f we have this 2xi and 2yj divided by 12. So, this is 1 over 6 xi plus yj. So, this is the n. Now, about the projection, because the surface this cylinder is in the direction of z. So, it should be noted that we do not have possibility now projecting this to any of the coordinate planes, because if we project, for instance, on xy plane, what will happen? Xy plane, the p, the perpendicular to this xy plane is the k, and when we do this product of n and k, which is needed there, so this will become 0, and that is coming in the denominator in our integral. So, this is not going to work, and again if looking at the projection also of this cylinder on the xy plane, this is going to be just a part of the circle. So, there will be no indeed surface there. So, whatever ways the formula will not work, and here also this is not, we cannot project it on this xy plane, because we will not get any surface on this, any plane on the coordinate planes. So, here we have to project it either on this xz plane, or we can project on this yz plane, then we can evaluate. So, what we have now, to summarize, first the grad f we have evaluated, that is 2xi plus yj, its absolute, the magnitude is 12, the given f is there, and the unit normal vector also we have now 1 over 6 xi plus yj. So, d sigma, that element on the surface, we can evaluate here the gradient f or gradient f and this p. So, this gradient f is 2xi plus 2yj and the p. So, here we are talking, if we take on yz plane, if we take the projection on the yz plane, that means the p will become I. We can do on xz plane as well, but it does not matter. So, we have taken here the yz plane, the p is I. So, this p is given now. So, we have d sigma equal to that 12 is given, which we have replaced here. The gradient f is 2xi plus 2yj, and so the gradient f was 2xi plus 2yj, and then p here, this vector, unit vector to the projected plane is I, we have taken. So, the dot product will give just the 2x and its magnitude 2x. So, that means we have 6 over x and this dA. Okay, therefore, what we have now, this surface integral f dot n d sigma can be evaluated with this. So, f dot n. So, from here we need to compute f dot n, that means 1 by 6 will be there, and then we have x z square, and from here we have x y square. So, 1 over 6 x z square and x y square, and this d sigma, where is d sigma is we have evaluated, that is 6 over x, and then we have dA, and we are projecting on y z plane. So, the projection, if we have to see that, again it will be a rectangular shape, because we have already seen in one of the previous example, we have the circular, we have the cylinder there, and if it is projected on the y z plane, it is going to be a rectangle here. So, for example, x z plane we have chosen. So, this is going to be rectangle, z is varying from 0 to 4, and then from the given equation we can find the coordinate of x as well. So, having this, we can now go with this limits. So, limits for z 0 to 4, and the y we will compute from this y axis. So, that is for y, we are projecting on y z plane, but same thing can be done for x z. So, y is moving from 0 to 6, and then we can evaluate this. So, here y with respect to y, we have y cube by 3, and then we have z square, and then y there with respect to y. After this evaluation, we can then evaluate with respect to z, and finally, we will arrive here at the answer, which is 416 in this case. Well, so these are the references we have used for preparing these lectures. Coming to the conclusion, so we have this surface integrals, mainly this f dot n, this flux in the direction, or the component of f in the direction of n is integrated over the surface S, and it has several applications. Some of them we have named already in the lecture. And how to evaluate, the idea is exactly what we discussed for evaluation of the surface area indeed, and this d sigma will be replaced by this grad f over grad f dot p. The p will be the normal to the projected plane. So, we have to project the given surface in one of the coordinate planes, and that depends on, so that this grad f dot p, the grad f dot p should not be 0. So, the gradient of f is the normal to the surface. So, normal to the surface should not be perpendicular to the normal to the projected plane, otherwise this will become 0 and we cannot use this formula. So, that we have to see that which one is convenient, and also this should not be 0 for the during this evaluation of this area integral. So, this surface integral is converted to the simple double integral, which we studied already, and then this simplification leads to another the simple formula which can be used for the surface integrals. So, so far we have learned the line integrals and the surface integral. The last these 3 lectures were devoted, one for the line integral, now for the surface integral. So, the next lecture is going to be again the conversion from the line to the surface integral. If you remember, we have already discussed the Green's theorem, where this such a conversion took place, that we have the curve integral, the line integral, and which was transformed to the double integral. And now we have more general, instead of double integral, the idea of the surface integral. So, we will generalize this Green's theorem, which is called Stokes theorem, one of its generalization, that will be discussed in the next lecture. So, that is all for this lecture, and thank you very much for your attention.